All right, so we are recording, my friends. So let's take a look at our first slide here before we go over our warm-up. So today is Monday. Happy Monday, everybody. You do have some homework that's due. You have some homework on chapter 11. This is information that is on your test on Wednesday, and we finished up probably last Monday or Tuesday. So hopefully you have that all done. You have some sections in chapter 12 that you need to do. And then you have a couple of sections in chapter 17, which you need to have done for tonight as well. And all of these things contain information that we finished up last week. So many of you already have your homework done for today, and that certainly takes a little bit of stress off of you if you don't wait until Monday after class to try and get all your homework done and your labs done, because that's a little bit of a pressure to get all that done at once. You do have a lab on colligative properties, which is also due for tonight. And again, many of you have done that lab already. And again, kudos to you to kind of keep ahead of the schedule a little bit. It will certainly make life a little bit easier or less stressful for you as we go through the course, because as we move along, the content does get a little bit harder, and especially the last week and a half, there's a lot that you need to do. So, the more you keep on top of your due dates and maybe even a little bit ahead of your due dates, the better off you're going to be. We have class tomorrow, and then you have a test on Wednesday. The test on Wednesday is on chapter 10 and chapter 11, which is content that we finished up probably the beginning of class last Tuesday. And you have completed your homework on, and we've done some practice problems on already. So hopefully you're getting yourself kind of ready for that. So let's switch over to the document camera. We'll take a look at our warm-up. We were given a set of data that contains 4 different trials. The concentration of A and the concentration of B are given to us for each of the different trials. And then the initial rate of the reaction is measured for each of those trials. And what we want to do is we want to figure out what the rate law is for this particular reaction. So how does the concentration of A affect the rate, and how does the concentration of B affect the rate? And then once we calculate or we figure out what the rate law is, we can take one of the trials, plug in the data, and calculate the rate constant or calculate K. And then along with that, we want to focus in on what the units are. So let's check and see how you did. Let me change to my document camera. Okay, and then let me just autofocus it just a little bit. All right. So let's take a look at our data. And what I did is I compared trial 1 to trial 3 in order to figure out what order A is in the reaction. And the reason I chose trial 1 and trial 3 for this part is that when I compare trial 1 to trial 3, the concentration of B is a constant. It doesn't change. K is also a constant. I'm doubling the concentration of A, and that doubles my rate. So I can calculate the order A is in my reaction. 2 to the M power equals 2. M has to equal 1. So that means that A is a first order reactant. And I don't really have to put this 1 in here. I just did it for emphasis. It's assumed to be there, so you don't necessarily have to do that. Then what I did is I looked at trial 1 and trial 2 to find out what order B is. Because by comparing trial 1 to trial 2, this time the concentration of A doesn't change, or it's a constant. K is a constant. So what I do to B is going to affect my rate. And if I compare trial 1 to trial 2, I'm doubling the concentration of B, and that's quadrupling the rate. So 2 to the n power, that's my order for B, equals 4. N equals 2. So B is a second order reactant. Now, it didn't ask this, but my overall reaction is a third order reaction because I just add up the orders for each of the reactants. So 1 plus 2 gives me 3. So the overall reaction is third order. Now, to calculate K, I just picked trial 1. It doesn't matter which trial you pick, K is a constant. I plugged in the concentration for A for trial 1. I plugged in the concentration for B for trial 1. Now, I have to remember the orders. A is first order. B is second order. Okay, so that means I'm going to have to square this number in order to calculate K. So I'm going to divide both sides by 0.185 molar. And then I'm going to divide both sides by 0.133 molar squared. That's going to give me 0.102 for my number for K. And then I'm dividing by my molarity. That's going to cancel out my molarity here. And then I'm dividing by molarity squared. That's going to give me 1 over molarity squared over seconds. Or we might see it this way. Since molarity is moles per liter, that's the same thing as saying liters squared per moles squared per second. Okay, you can write it either way. This is more consistent with the units that were in the table, but this is something else you might see in some of the questions that you're working on. So, questions on how we worked this out? We feel fairly confident. Now, maybe this was a little bit easier than what some of the questions might be, because it was pretty obvious that A is first order, and it was pretty obvious that B was second order. If it's not as obvious, then you're going to be taking the natural log of both sides so that you can figure out what that exponent number is. Most of the time, though, it's pretty straightforward. And most of the time, your reactants are going to be 0 order, first order, or second order. Those aren't the only orders, but they're the most common ones.
So I know with second order, you square it, but what happens when you get to third order and fourth order? Or are we not going to cover that?
Well, you're not likely to see that. And we're actually going to talk about that a little bit more towards the end of today's class. But in order to get like a third order reactant or reaction, you're essentially saying that 3 particles have to come in contact with each other all at the same time and at the same orientation and with enough energy to react in order for the reaction to take place. And that's pretty unlikely. Does that make sense?
Yeah, okay. So
Yeah.
we just won't typically have to see that in any of
No,
the...
you will not see that at all. And it's highly unlikely that it would even happen. But it's we'll talk about that a little bit more later on. My dog is dreaming in the other room. We'll talk about that a little bit more at the end of today. But yeah, it's not something you're going to calculate.
Okay, thank you.
All right. Any other questions before we switch back? Okay. Sorry about that. He's really having a dream in the other room. Jeez, I don't know if you can hear him, but he's pretty loud. Okay, so let's spend a couple minutes and go through the test, which is on Wednesday. And again, we don't have class on Wednesday, but I will open up the test so it'll be available to you at 11 o'clock on Wednesday, and I'll leave it open till 8 o'clock Wednesday night. And once you open up the test, it is timed. So as soon as you open it up, the timer starts. So you kind of have to make sure you have enough time to finish the test. So you can't start the test at 8 o'clock. It closes at 8 o'clock. So just kind of keep that in mind. So there are really 3 parts to the test, but kind of only 2. So the first part of the test is more like definitions, multiple choice, drop-down menus, matching, those kinds of questions. There are 12 questions in part 1. And once you start, you have 25 minutes to finish those 12 questions. It's also set up so that after you finish question 1, you have to submit it before you can go on to question 2, and you can't go back to question 1 once you're finished. Okay, so once you've submitted it, it's submitted and you need to move on to the next question. Things that you should focus your time on. Intermolecular forces. Okay, so you need to remember that we have London forces, which are the weakest type of intermolecular forces. We have dipole intermolecular forces, and we have hydrogen bonding. And hydrogen bonding is the strongest of the 3 types of intermolecular forces. And remembering that intermolecular forces are much weaker than intramolecular forces that hold atoms together in a molecule. So you need to know kind of what the different types of forces are. You need to remember that the London forces are the weakest, dipole is a little bit stronger, and hydrogen bonding is the strongest of the intermolecular forces. And that helps you to determine physical properties. So like boiling point, the stronger the intermolecular forces, the higher the boiling point, okay? Or freezing point. The stronger the intermolecular forces, the higher the freezing point. Or vapor pressure. The stronger the intermolecular forces, the lower the vapor pressure, because less particles can become a gas above the liquid. Intermolecular forces are related to solubilities. So when you look at solutes, they tend to dissolve in solvents that have similar intermolecular forces. So if water is your solvent, it's a polar solvent, it tends to dissolve polar solutes. The more polar the solute is, the more soluble it would be, okay? General things about intermolecular forces. We went through a little bit on heat, and we talked about the fact that heat energy can be added to a substance to change the temperature, and it can be added to a substance to change the phase. So we had our equation here, which actually you worked a little bit with in Chem 1, where the amount of heat or energy that's required to raise the temperature of a substance equals its mass times the change in temperature times the specific heat of that substance. Okay, when we talk about phase changes, there should be an H here. I think I copied the delta and then forgot to put an H here. So it would be the amount of energy that's required to change the phase of a substance equals the number of moles of that substance times the enthalpy of vaporization or the enthalpy of fusion values. So again, there should be an H here. It should say delta H. Typically, you're given the amount of a substance in grams, so you need to remember how to do gram mole conversions in order to do a question like this second type. Phase diagrams, so how pressures and temperatures affect phases. So when is it a solid, when is it a liquid, when is it a gas? Where is the triple point on a graph? Where is the critical point, and what does that mean? So there might be a graph that you have to identify, different phases in that graph. For types of solids, we talked about amorphous versus crystalline solids. And crystalline solids have those unit cells that have particular things at their lattice points. So when we talk about when we talk about crystalline solids, they can be ionic if there are ions at the lattice points. They can be atomic if there are atoms at the lattice points, or they can be molecular if there are molecules at the lattice points. And when we talk about atomic solids, you can be looking at metallic or network covalent solids within kind of this category. I will tell you that you do not have to differentiate the different types of unit cells, and you don't have to do any kinds of calculations about the number of particles that are in those unit cells. So that part really isn't on the test. You have to know a little bit about concentration. So calculating the molality of a solution, which is moles of solute per kilogram of solvent. Okay, calculating the molarity of a solution, which is moles of solute per liter of solution. Calculating the mass percent of a solution, which is the mass of the component you're looking at over the total mass of the solution. Or mole fraction is the moles of the component you're looking at over the total moles in the solution. And then knowing generally about colligative properties. So knowing that when you add a solute to a solvent, the boiling point is elevated. Or when you add a solute to a solvent, the freezing point is lowered. Or when you add a solute to a solvent, the osmotic pressure decreases. Or when you add a solute to a solvent, the vapor pressure of the solution goes down. And knowing that there's a difference in these colligative properties depending on whether the solute is an electrolyte or a non-electrolyte. If it's an electrolyte, that means it breaks up into ions in solution, and that's going to multiply the effect of dissolving that solute in the solvent. If it's a non-electrolyte, it doesn't break up into ions in solution. So the effect will not be as great as if it were an electrolyte. So these are the kinds of things that you're going to see in part one. Very little calculating in this part. There's a little bit, but very little calculating in this part. So there's nothing you're submitting work-wise for part one. Okay, when you're finished with part one and you've submitted that, then you go on to part two. Part two has 6 questions, and you have 45 minutes to answer those questions. And the reason for that is these are going to be longer questions that you're going to have to show all your work on. So there'll be a place for you to submit your answer for each of the questions in part two. But then you're also going to be submitting your work, and you won't be getting credit for the answers in part two unless you submit your work for part three. So make sure that you can do the calculations for the various types of concentration. So molarity, molality, mass percent, and mole fraction calculations. Okay, they could be real kind of general questions where you're given the information to calculate the components and you're just asked to calculate, let's say, the molality. Okay, or you're given the information, you're asked to calculate the mass percent. Or the questions could be a little bit more involved where maybe you're given the mass percent, and from that information, you're asked to calculate the molality. Or maybe you're given the molarity of the solution and you're asked to calculate the mole fraction of the solution. Okay, there'll be questions on colligative properties where you'll have to calculate how much does the freezing point go up when you make a solution, or how much does the or boiling point go up? How much does the freezing point go down when you add a solute to a solvent? Or how does the osmotic pressure change when you add a solute to a solvent? Or how does the vapor pressure change? So we have our vapor pressure here. If we have our pure solvent, we multiply it by the mole fraction of the solvent, and that would give us the mole fraction of the solution. Actually, I wrote osmotic pressure there twice. You only needed to be there once. Once you're finished with part two, then you would submit your answers in part two. And then in part three, you just open up part three, submit the work from part two into part three, and then submit part three. Okay, and that'll be timed, but I think I gave you like 10 minutes to do that. And you've practiced, how to upload documents in various different things that you've done already. So 10 minutes should be more than enough time for you to get those documents submitted. So questions on the format of your test? Everybody okay? Again, I don't want there to be any surprises. I want to be as open as possible so that, you can do the very best that you possibly can on your test without, the anxiety of, I don't know what's going to be on the test and I don't know what the test is going to look like. The first time it's always a little bit hard anyway to take a test for a new professor, but hopefully this clarifies things just a little bit. So here's 2 practice problems. We did a couple of practice problems last week. We're going to do a couple more practice problems now. So I'm going to give you a couple of minutes. You have an osmotic pressure question that you need to do, and then you have a vapor pressure that you need to do. And let's see how you do with that. Again, you've already done the homework on this, so hopefully you're a little bit stronger on doing these questions, and then we will go over them. So I'll give you maybe 8-10 minutes. Remember that when you do your osmotic pressure, R is your gas law constant, which you're using 0.0821 liters ATM per mole Kelvin, and make sure that all your units are consistent when you do that. And when you get your answers, let's put a couple of them in the chat just so that I know that we're done and that we're ready to go over it. Good, we're getting some consistency. Good. Okay, another minute or so. Yeah, let's get a couple of answers in there for the second one as well, just to make sure that we can check and see if we're all agreeing with the answer. All right, do we have any more answers to the second question before we go on? Or do we still need more time?
I think I need another minute for the second
You
one.
got it.
Thank you.
All right, my friends. So I'm going to stop sharing this. Let me put up my document camera. And let's look at that first question, which we did get. Oops, what happened? We did get quite a bit of consensus on the answer to the first question, so that's good. So the question gives us the osmotic pressure for a solution, and it gives us the temperature that that solution is at. We can calculate the concentration of the solution in terms of its molarity. So osmotic pressure equals the molarity of the solution. It's a capital M as opposed to molality, which is a lowercase m, times our gas law constant times our temperature. Okay, temperature has to be in Kelvin so that that cancels out. Since the pressure was given to us in ATM, we want to make sure that we use the constant that's got ATM in it. We're going to divide by R and divide by T, and we get the molarity to be 0.182. And molarity really is moles of solute per liter of solution. So if we multiply both sides by liters, we can calculate the moles of the solute. So we take the molarity times the volume, although it was given to us in milliliters and we need to convert it to liters, we can calculate the moles of the solute that we added to the solution. It told us that the solute was C6H12O6, which is glucose. And it gave us the molar mass, which is how many grams there are per mole. So we can do a conversion from moles to grams. And since we had 3 significant digits that were given in the question, we want to make sure that we have 3 significant digits in our answer. So questions on the first problem that we did. Again, there was quite a bit of consensus in the chat on the answer, so that's pretty good. All right, so that's an example of an osmotic pressure problem. Let's look at an example of a vapor pressure problem. Okay, so it told us that we have an alcohol as our solvent. It doesn't tell us what the alcohol is. It doesn't matter because it gave us the molar mass of the alcohol. So the first thing we want to do is convert grams of our solvent to moles of our solvent. And since we've got 4 digits here, we really should have 4 digits here. Once we know the moles of the solvent, and the question gave us the moles of the solute, we can calculate the mole fraction of the solvent. That means we're going to take the moles of the solvent and divide it by the moles of the solute plus the moles of the solvent. And that's going to give us a mole fraction for the solvent of 0.688. And there are no units for that. It essentially is saying it's 68.8%, but we just leave it in the decimal form because we're going to use that number to calculate what the vapor pressure of the solution would be. And we do that by taking the vapor pressure of the pure solvent, this was given to us, multiply it by the mole fraction of the solvent, and that'll give us the mole or the vapor pressure of the solution. And notice that the vapor pressure goes down as we add the solute to the solvent, because essentially those solute particles form intermolecular forces, hold on to the solvent particles and prevent them from becoming a gas. So the vapor pressure would be lower. And the units are torr. It's just another unit for pressure. In Chem 1, you talked about, in your gas law unit, all the different units for pressure. So how do we do on that? Sometimes it's good when you're given some time to work out a problem on your own. And then when we go over it, you can say, oh yeah, I did this, or I had this small part that I did wrong. Make sure that you put little notes next to that so that when you go to see those questions again, you won't make the same mistake twice.
I need some help.
Yes.
I'm really struggling to get from, with the osmotic pressure problems, to get from, it's asking for like the moles of like a substance. It won't tell you what it is, but it gives you the volume, pressure, and temperature.
So if it gives you the pressure and it gives you the temperature, you can calculate the molarity of the solution from your osmotic pressure calculation. And then if you know the volume, you can calculate the moles of the solute. You won't be able to calculate the grams if it doesn't tell you what the substance is.
Okay,
Does that help?
I think so. So, okay, so you are supposed to multiply the molarity by the liters to get moles.
Yes, in order, so molarity equals moles of solute per liter of solution. So if
Okay.
we want to calculate moles, we're going to have to multiply both sides by our volume to get moles by itself.
Thank you.
You're welcome. Any other questions? Again, I'm here to help. So if there's something you're not sure about, make sure that you ask when we're going over this stuff. All right. So we are going to move on in chapter 17. Remember that chapter 17 is not stuff that's on your test on Wednesday. It will be on your test next Wednesday. But what we have talked about so far in chapter 7 is rate laws. And essentially, when we deal with rate laws, what we're dealing with, let me get my little thing back up here, is we are dealing with how the rate of a reaction changes with changes in concentration. Okay, so if we were to double the concentration, how does that affect the rate? Okay, those are our rate laws. What we're going to look at today is what's called an integrated rate law. And it's a little bit different. The integrated rate law looks at how the concentration of reactants changes over time. Okay, so rate laws are how concentration affects rate. Your integrated rate law is how the concentration changes over time. So if we were to look at a first order reaction, we have reactant A producing product B. Okay, we could calculate the rate by taking the change in the concentration and dividing it by the change in time. And again, that value was a negative value because A is being consumed as the reaction proceeds. Now, we learned from our rate laws that we can also say that rate equals K times the concentration of A. So what that enables us to do is set these two equations equal to each other. Okay, we've got rate here and we've got rate here. So we can just set these two equations equal to each other. And now we have the change in concentration over time equals K times our concentration of A. Now, using calculus, which we're not going to be doing, so we're not going to be going through where this is derived from, but it's going to give us how the change in the concentration is changing over time. So it leads us to these two integrated rate law equations. So if a question tells us we're looking at a first order reaction and it deals with concentrations and time, these are the equations we're going to be looking at. So the natural log of the final concentration over the initial concentration equals negative KT. We'd want to use this equation if we know what the initial concentration is and what the concentration is after a period of time. Or we could manipulate this equation just a little bit and get something like this, where we can find out what the concentration of a reactant will be after a period of time. If we know what the initial concentration is, and we know what the rate constant is, K, and we know what the time is. Now, brackets mean concentration. So the concentration of A after time T is what this stands for here. As compared to this is the concentration of A initially at the beginning. So if a reaction is a first order reaction, these are the two equations that we're going to be using. So let's look at a couple of practice problems, and I encourage you to practice plugging the numbers into the calculator just to make sure you know what you're doing. So if we were to look at this one, it says the decomposition of N2O5 to NO2 plus O2 is first order. It's going to tell us that, at least for now. And the rate constant, this is K, is 4.800 times 10 to the minus 4 reciprocal seconds. So it gives us K. If the initial concentration of N2O5 is 1.65 times 10 to the minus 2 moles per liter, or that's the molarity of that gas, what is the concentration after 825 seconds? So it's giving us an initial concentration. It's giving us K. It's giving us the time. And it's asking us to calculate the concentration after that amount of time. So this is the integrated rate law equation we would want to use in order to calculate what the concentration will be after 825 seconds. So we're going to plug in our numbers. The initial concentration is 1.65 times 10 to the minus 2. So we were given this number. Okay. E is just a button on your calculator. It's a function on your calculator. If you find the LN button on your calculator, for pretty much all calculators, the second function of that button is your e to the x button. That's what you want to be using for this function here. So you would push the second and then that LN button, okay, and then 4.800 e negative 4 times 825, okay, that'll give you this part, and then multiply it by 1.65 e negative 2. Plug it in the calculator because order of operations is important. And make sure that you get 0.0111 for an answer. So second, that LN button, negative 4.8 e negative 4 times 825 equals, and then multiply that by 1.65 e negative 2. And make sure you're getting 0.0111. We don't want the calculator to be in ignorance when we can plug the numbers onto the paper. We just can't get the right answer. Okay, so what does that mean? Well, it means that the initial concentration of this reactant was 1.65 times 10 to the minus 2, just as the reaction was starting. But after 825 seconds, only 0.0111, which is really 1.11 times 10 to the minus 2 moles per liter will be remaining. The rest of it reacted during that time period. So how do we do with order of operations and getting that into a calculator? Anybody having any problems with that? Kind of have to take it one step at a time and make sure that you recognize that there's a negative sign here. So it's e to the negative k times t and then we're going to multiply it by the initial concentration, and that will give us the concentration after that period of time. So let's look at another one. Okay, we're going to look at the same reaction, but it says the gas phase decomposition of N2O5 at 335 Kelvin is first order. Okay, it's telling us that. So we know the integrated rate law equations that we need to use. When the initial concentration of N2O5 was 0.199 molar, the concentration of N2O5 dropped to 5.27 times 10 to the minus 2 molar after 217 seconds. Calculate the rate constant. Okay, well, this time we know the initial concentration, it's given to us. We know the concentration after a period of time, and we know the temperature. We want to calculate K. So in order to do that, it would be easier to use this form of a first order integrated rate law problem, because we've got our final concentration and our initial concentration already on the same side of the equation. It's a little bit less we have to manipulate. Now we're trying to calculate K. So that means we need to get rid of negative T on the right-hand side of the equation, and we would do that by dividing by negative T. So K equals the negative, again, that comes from the fact that we want to get rid of negative here, negative ln of the final concentration over the initial concentration divided by the time. Now that we have the equation the way we want it to be, we know the concentration after 217 seconds. We know the initial concentration at the beginning. We know how long it took to get that temp or that concentration change. We want to calculate K. So here are our numbers. We're going to take negative ln of 5.27 e negative 2 divided by 0.199 divided by 217. So again, you can just find that ln button on your calculator. It's a function on your calculator. It's usually below the log function on a calculator, not always, but usually. So plug that in, order of operations, and we want to calculate K. And again, don't just take my word for the answer when I put it up there. Plug it in the calculator so that you can say, okay, I know how to plug this in the calculator, or you're like, I don't know where that number came from. So negative ln 5.27 e negative 2, sorry that should be an exponent, it's not, divided by 0.199 divided by 217. Okay, the calculator should say, if we plug it in the right way, 6.12. Again, we want 2 significant or 3 significant digits because that's what we're given in the question. The calculator will probably say e negative 3. Make sure that you pay attention all the way over on the far right-hand side of your calculator so that you don't miss this part of the number. And then the units for K for a first order reaction is reciprocal seconds, 1/seconds, or it might say s to the -1 power, means the same thing. Again, the key is looking at the question and it's identifying that it's first order, looking at the information you're given and what you're asked to solve for, and then which one of the first order integrated rate law equations will help you the best. All right, so let's look at another one. Same kind of problem, worded just a little bit different. Okay, it tells us that we're looking at a first order reaction. Okay, it's giving us that information. It's one of those two equations when we're looking at integrated rate law. It gives us K, 0.0079 reciprocal seconds. We want to calculate time, how long will it take, for the reactant to be reduced to 60% of its initial concentration. So it doesn't give us like wording. It doesn't give us the initial concentration and the concentration after a period of time, but it tells us that 60% of that reactant is reacted during the period. So it's a ratio. So let's say that we start with 100. Okay. If we're going to get reduced to 60, okay, we know what our final is. Okay. So we're going to use 160 for our initial concentration and our concentration after our time period. And it's better to use this equation here than the other version because you have the concentration after the given amount of time. You have the initial concentration, not in so many words, but you can figure it out. You're given K and you want to calculate T. So if we want to calculate K, we're going to have to divide both sides. Oh, sorry, we want to calculate T this time. To calculate T, we're going to divide both sides by negative K. So the time it takes to get to 60% of the initial concentration would equal negative ln of the final concentration over the initial concentration divided by K. Okay, so we don't know what the actual concentration is after the time period and what the initial is. But if it's 60% reduction, we started with 100 and we end up with 60. It's a ratio, so it doesn't matter what numbers we really put there as long as we make them 60%. We'll divide it by K and we get 65 seconds. Now, if you plug that in and you get negative for a time, that doesn't make sense. Okay, you can't have negative 65 seconds it takes for a reaction. So go back and say, oh yeah, I forgot that negative sign there. And there's my 65. So it took 65 seconds for the reactant to go from 100% down to 60%. Different variations of first order integrated rate law problems. So let's look at one same kind of problem. Okay. It says the initial concentration of ethyl chloride is 0.00100 molar. After heating at 500 degrees Celsius for 155 seconds, the concentration was reduced to 0.000670 molar. What is the concentration after 256 seconds? Well, this question is actually going to have two parts to it. The first part, we have the initial concentration, and we have the concentration after 155 seconds. So what we can do is we can calculate K for this reaction, and that's what we need to do first. And then once we know K, we can take the initial concentration and K and our new time to calculate the new concentration. So let's take a look at those parts. Our first part, okay, we're given the initial concentration. Again, that's what this 0 means. The initial concentration is 0.00100. The concentration goes down to 0.000670 in 155 seconds. So let's calculate K. All the numbers you need to plug into this equation, plug them in, and calculate K. Let's do that part first, and then we'll use K in the second part. So plug the numbers in and calculate the rate constant. So take negative ln 0.00067 divided by 0.00100 equals, and then divide it by 155. And remember that negative sign in your equation. Okay, so I'm getting 2.58 times 10 to the minus 3. Now, remember that this is seconds. These units cancel out. This is seconds, so we end up with 1 over second, so reciprocal seconds for K, and those are always going to be our units for the rate law constant for first order reactions. Now we know K. We're going to go back and find out what the concentration is after this time period. So we know the initial concentration. It's the same reaction. So the initial concentration is 0.00100. Now, time equals 2.5 or 256 seconds. We know K. We want to calculate the concentration after 256 seconds. So we know the initial concentration. We know K. We calculated in our first part. We know T, which is now 256 seconds. We're going to plug all those numbers into our equation, plug it into the calculator, and we're going to calculate what the temp or the concentration will be after 256 seconds. And again, I'll give you a couple quick minutes, see if you can calculate, plug those numbers into the calculator. Remember that this is a function on the calculator. It's the second function of the ln button on your calculator. Okay, don't forget this negative sign in here either, or that's going to screw up your concentration. And you should expect the concentration after 256 seconds to be less than what the concentration was after 155 seconds. Again, because as time progresses, the concentration of the reactants is going down. All right, so I'm getting 5.17 times 10 to the minus 4. So find the E button on your calculator. And it's E to the X. So this is your X here, negative 2.58 E negative 3 times 256 equals. That'll give you this part of the equation. Then you're going to multiply it by the initial concentration was that 0.00100. Okay, I have the right answer in there, right? Sometimes I don't. Negative 2.58 E negative 3 times 256 times 0.001. Yep. All right. So how do we do with first order integrated rate laws? There's two equations. Okay, if the question deals with changes in concentration and gives you times, now this is what you want. What we did last Thursday did not talk about times, it was talking about rates. a different kind of kinetics problem. All right, so second order rate laws. Okay, the question would say, at least for now, that it's a second order rate law. Okay, well, we know that we can calculate rate by taking the change in the concentration over the change in time. And we know that for second order rates, it equals K times the concentration of A squared, second order. Okay, now, again, we're not going to use the calculus. I'm just telling you that this is how this happens. We can relate time and concentration. So this is a second order integrated rate law. Okay, it's different than our first order. So we've got the inverse of our final concentration equals K times T plus the inverse of the initial concentration. So if the question talks about second order rate laws, second order reactions, this is the equation we'd want to be working with. Again, I'm not going to ask you to use calculus to derive it. I'm just telling you that calculus was used to take this equation and derive this equation, but we don't have to worry about where it came from. Again, this means the concentration after this amount of time. And this means the concentration at the beginning, the initial concentration. So we looked at first order. We just looked at second order. So now let's look at zero order reactions. So again, we know that we can calculate rate by taking the change in concentration over the change in time. And again, this negative is just because the reactant is decreasing in concentration as time progresses. And for zero order, we know that rate equals K times the concentration of A to the 0 power. But any number, no matter what this value is, any number to the 0 power is 1. So really, this here just equals K, because this part equals 1. So again, using some calculus, we're going to get our third integrated rate law equation. This is for zero order reactions. If the question tells us it's a zero order reaction, the final concentration after a period of time will equal negative K times T plus the initial concentration. Okay, and again, we know that this means the concentration after T. This means the initial concentration. Now, when we look at those first order reactions, okay, this was an equation that we had. We actually manipulated it a little bit. It was actually ln of the concentration after time divided by the initial concentration. This is just another way of writing it. So look at the way this is written, okay? We could actually write it as y equals mx plus b. That should look familiar to you. That's an equation for a straight line. So ln of the concentration after a period of time would be y. The slope is negative k. X is the time, and the y-intercept is the initial concentration. So this is in the form of y equals mx plus b. So now we're going to look at some graphs. If we were to plot the natural log of the concentration after a period of time versus time, we're going to get a straight line. And the slope of that line is going to equal negative k. Now, we can do the same things for zero order and second order. So if we take concentration versus time, and we get a straight line, we're looking at a zero order reaction. If we took the natural log of concentration versus time, and we get a straight line, it's a first order reaction. And if we take the inverse of concentration versus time, and we get a straight line, it's a second order reaction. It's just taking those integrated rate law equations that we looked at, putting them into a y equals mx plus b form, and seeing which graph gives us a straight line. Zero order if it's concentration versus time, first order if it's natural log of the concentration versus time, and second order if it's an integrated, if it's the inverse concentration versus time. So it is about 7:15. Let's take about a 4 or 5 minute break. We'll come back, let's say about 7:18, 7:19 or so. So get up, take a little bit of a break, go to the bathroom, get a drink, stretch just for a couple of minutes, and then we'll come back and look at these kinds of graphs just a little bit more. All right, another minute or so, we'll get ourselves settled back in and finish up our class. All right, my friends, let's get ourselves started back up again. So, oh, I don't want to do that yet. Oop, do it. Okay. So let's say that we were to run a lab and we're looking at the concentration of N2O5 as time progresses. And we collect data in these two columns. So just as the reaction starts, the concentration is 0.09996. And after 50, there's no units there, but let's say it's seconds. That's what's on the graph. So 50 seconds, it's 0.07072. And then after 100 seconds, 200 seconds, 300 seconds, 400 seconds. So here's our data for how the concentration changes as time progresses. And we were asked, what order is the reaction? Well, what we would do is we would graph concentration versus time. And if we graph that, we would get something like this, where we've got concentration along the y-axis and time along the x-axis, and we plot the data, and it's not a straight line. That tells us that the reaction is not zero order. So then we take these values, we use our calculators, and we calculate the natural log of each of those numbers. So the natural log of 0.09996 is negative 2.308. And the natural log of 0.07072 is negative 2.649, and so forth down through the table. And then we graph the natural log of the concentration versus time. And when we do that, that gives us a straight line. That tells us the reaction is first order. You know, we can verify that it's not second order by taking the concentrations and finding the reciprocal of those numbers. So 1 over 0.09996 is 10. 1 over 0.07072 is 14.14, and so forth down. And then if we were to graph the inverse concentration versus time, it's not a straight line, so it's not second order. So here's zero order, here's first order, here's second order. The one that gives us the straight line tells us what order the reaction is. So this reaction is a first order reaction. We can determine the order graphically by graphing concentration versus time, the natural log of concentration versus time, and the inverse concentration versus time. And the one that's a straight line is going to give us the order for the reaction. Now, half-lives. When we talk about half-lives, it's the time it takes for half of a reactant or a reagent to be consumed or to react. Okay, it can be written as T 1/2, or we could say if we have the initial concentration and we multiply it by 1/2, that will give us the final concentration. So if we look at a zero order reaction, the half-life can be calculated by taking the initial concentration and dividing it by 2K. And actually what happens for a zero order reaction is the half-life decreases as the reaction progresses, because it has to do with the concentration that we're looking at. If we were to look at a first order integrated rate law, the half-life can be calculated by taking the natural log of 2, ln of 2, and dividing it by k. Now, ln of 2 is a constant. If you put it in the calculator, it's 0.693. So the half-life of a first order integrated rate law is 0.693 divided by k. Now, this all up here tells you how we derive the half-life. You're never going to be asked to do that. So we kind of boil it down to, here's the half-life. Now, a first order reaction, the half-life is not affected by the concentration. It's a constant. And if we were to look at a second order integrated rate law with respect to its half-life, the half-life equals 1 over k times the initial concentration. So with each successive half-life, it's going to double the time it takes to get to that half-life. So it's dependent on the concentration again. So if we wanted to graph that, if we were to look at a 0 order reaction, okay, and we start out with 0.200 molar for A, we get down to half that amount here, and then we cut the amount in half again going to here, and then we cut the concentration in half again going here, and what we're going to notice is that the half-life gets shorter and shorter as the reaction proceeds. That's for 0 order. For first order, if this is our initial concentration, it takes this amount of time for us to get to half the amount. It takes this amount of time for us to cut the amount in half again. And it takes this amount of time to cut the amount in half again. And for a first order reaction, the half-life is a constant. Doesn't matter how much we have. It's always going to be the same if it's first order. And if we look at a second order reaction, if this is the initial concentration, okay, it would take this long to get to our first half-life. It would take this long to get to our second half-life to cut the amount in half. And it would take this long to get to our third half-life. If it's a second order reaction, the half-life actually increases with time. So the important thing, which you're most of the time going to be dealing with, are first order reactions when you're asked about half-lives, because it's independent of the concentration. It's 0.693 divided by K. So this table, I would suggest that you screenshot it or you print it out or you do something because it summarizes everything you need for 0 order, first order, and second order reactions. So if we look at rate law, sometimes this is called the differential rate law, but usually the word differential just gets dropped off. Rate laws, this is what we talked about last Thursday. If it's 0 order, rate equals K. If it's first order, rate equals K times A to the first power. And if it's second order, rate equals K times the concentration of A to the second power. Rate laws, which we determine from data given to us in a table. When we talk about K, the units for K are dependent on what the order is. So for 0 order, it's molarity per second. For first order, it's reciprocal seconds. And for second order, it's 1 over molarity seconds, or it's reciprocal molarity seconds. You can figure out the units for K by just plugging in the units into the rate law that you determine. Integrated rate law, okay? This is when time is talked about in the question. 0 order, okay, concentration after a period of time equals negative KT plus the initial concentration. Again, that's y equals mx plus b. So plotting concentration versus time, y versus x, would give us a straight line for zero order. The slope would be negative k, or k would be the negative slope. And the half-life is the initial concentration divided by kT. If it's first order, okay, it's the natural log of A equals negative kT plus the natural log of the initial concentration, or we plot y versus x, or the natural log of A versus time. If that gives us a straight line, it's first order, and the slope will equal negative k, or negative k, or k would equal negative slope. And for first order reactions, the half-life is independent of the concentration. So 0.693 divided by K. And if it's second order, it's the inverse concentration equals KT plus the inverse of the initial concentration. If we graph Y versus X, or the inverse concentration versus time, K will equal the slope. This actually is a positive slope as opposed to these two are negative slopes. And the half-life would be the inverse of the initial concentration versus K. So again, I would just either screenshot this screen or print it out and have it available to you. And then you just have to figure out what order the individual reaction is. And then you can figure out what equations you need from there. So let's do a couple of first order half-life problems. So it tells us that we have this compound that's decomposing, and it tells us in the question it's first order. Now, what the question could say is maybe it'll say the natural log of the concentration versus time is a straight line, okay? And it doesn't say first order. Well, that's what that means, okay? But it tells us it's a first order reaction, okay? It gives us the reaction. So it tells us, our temperature is 320 degrees Celsius. The rate constant is 2.20 times 10 to the minus 5 reciprocal seconds. So it's giving us K. And it wants us to calculate the half-life. How long will it take for half of this reactant to decompose? So since it's first order, okay, we know that to calculate the half-life, we would take the natural log of 2 divided by K. Now the natural log of 2 is 0.693. Okay, it's always going to be 0.693. So you could put that in instead. So to figure out the half-life, we're just going to take 0.693 and we divide it by K. So plug that in the calculator. Let's make sure that we can use our calculators without that being a problem, because a lot of times I see people, they're working out their problems. Everything's worked out well on paper, and then they get the wrong answer because they don't plug it in the calculator the right way. Okay, so ln2, which should be 0.693 on your calculator, divided by 2.20 e negative 5. Okay, and I'm getting 3.15. Ooh, what is that? Where'd that come from? 3.15 times 10 to the 4th. And my units, well, this is reciprocal seconds here. Okay, I'm just going to take the reciprocal of it, and that's where seconds comes from. And that makes sense because I'm talking about a time. So that means it will take 3.15 times 10 to the 4th seconds for half of this compound to decompose. Now, it doesn't matter whether I start with, let's say, 100 grams of the substance. Okay, it's going to take this long for me to get down to 50. Or if I were to start with 1 gram of the substance, it would take this long to get to a half a gram. So it doesn't matter how much I'm starting with. If it's a first order reaction, my half-life is a constant. It's independent of my concentration that I'm starting with. All right, so let's look at this one. Okay, we have a reaction. It's a generic one. Here's the important part. It says it's a first order reaction. So we know half-life equals 0.693 over K. This time it tells us what the half-life is. It's telling us how long it takes for half of this reactant to decompose. If the reaction is starting with 60 grams, how many grams will you have after, or how many grams will you have left after 55 minutes? Now, here's an issue. This is talking about minutes, and this is talking about seconds. So we have to make sure that the units match up first before we can plug them into the problem. And since we're given the half-life and we're told it's first order, we can calculate K. And once we calculate K, if we know how much we're starting with, we can find out how much we end with after a period of time. So the first thing we want to do is calculate the half-life. Okay, so we know our equation. We're calculating K. So that means we're going to have to multiply both sides by K and divide both sides by our half-life. So here's our equation. Remember, the natural log of 2 is 0.693. So 0.693 divided by 1800 is going to give us K. So that's our first thing, calculate K. Again, I strongly suggest that when you do this, you actually plug it into the calculator to make sure that you know what you're doing. Don't just say, oh yeah, she put down that that's what the answer is, and I'm just going to assume that's what it is. Okay, we do have a whole bunch of consensus. Okay, so I'm taking the natural log of 2 divided by, now I'm going to have to convert this to seconds. So 55 times 60, that'll get that to seconds. And you can do that in a separate step. So I'm getting 2.1 times 10 to the minus 4 reciprocal seconds. Why does that not, or is that the answer at the end? That can't be the answer at the end. So why are we not agreeing? So the natural log of 2. Oh, okay, we forgot to, there we go. Okay, so we just forgot to convert. So we're going to divide it by 55 times 60. Remember, the units have to match up. Okay, you could have gotten reciprocal minutes to begin with, and that's okay. Yeah, so I agree with that. Okay, so now that we have K, again, I guess you could have converted this. You could have come up with reciprocal minutes, and then you had to convert it to reciprocal seconds so that it matches up with the next part of the question. Okay, so now how much of A will be left over after a given amount of time? Okay, well, we calculated K. Again, I converted it to seconds here. I apologize that I really didn't clarify that. I thought I did. I changed it to reciprocal seconds because my time is in seconds. Oh, sorry, my time here. I'm going to have to convert. What did I do? Yeah, is in seconds. So my initial concentration is, initial amount is 60 grams. I'm going to multiply that by e to the negative K times my time. And you would have gotten the same answer had you left this in reciprocal minutes and then left this as minutes. It doesn't really matter. They just have to be consistent units. Okay, and we typically talk about K values in terms of reciprocal seconds, not reciprocal minutes. Just as a kind of standard thing. So again, practice putting that in the calculator. Find that E button. Okay, it's the second function of your ln on your calculator. So e to the x, where x is negative 2.1 e negative 4 times 3,300, and then multiply that by 60. It really doesn't give you the concentration, it gives you the amount, but it's the same thing. The units are all going to be the same. And you're going to find out how much you have after 55 minutes. And you would certainly expect that the answer is going to be less than 60. Okay, just so that in your head, you're saying, well, the reaction is progressing after 55 minutes. I'm going to expect to have less than 60 grams. So plug that in, see what you get for your concentration after 55 minutes. All right, so I'm getting 30.0 grams. Good, excellent. And that is the half-life, I agree. Just happens to be for this question. Yep, so you figured out the half-life. But you didn't know that to begin with. All right. So let's look at another one. All right. So we've got our reaction. It tells us it's first order. Okay, it tells us that the half-life is 12.0 seconds. I don't know why starting isn't spelled right, but we're starting with 0.500 molar. How much will we have after 48 seconds? Okay, so think about what you have to do. You're going to want to calculate K. Actually, we're going to do it an easier way. Let's do it an easier way. Let's do this an easier way. Okay. If the half-life is 12 seconds and the reaction goes for 48 seconds, this is actually kind of easy. We can figure out how many half-lives have gone by. Let's do it that way. Okay, so if we start out with 0.500, after one half-life, which is 12 seconds, we would have 0.500. After two half-lives, we would have 0.1250. We're just cutting this in half. After three half-lives, we would have 0.0625. And after four half-lives, we would have 0.0310. Okay, we could do it that way. What we also could do is we could take 1/2 to the n power times our initial concentration, where n is the number of half-lives. Well, if we take 48 and divide it by 12, 4 half-lives have gone by. So we've got 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. And 1/2 to the 4th power times 0.500 gives us 0.0313. We can calculate it this way. We could calculate it this way. We even could have calculated it maybe a harder way by calculating K and then using our first order integrated rate law equation. And we could calculate the concentration after the particular period of time. Okay, take the initial concentration times e to the negative KT. They're all related when we're talking about half-lives. This is kind of an easier way. Maybe if you were looking at a short answer kind of a question on a test, you know, you could do it this way, or you could do it this way, or you could verify an answer doing it that way. All right, so let's talk about collision theory. Okay, how or why do reactions take place? So when we talk about the rate of a reaction, it is proportional to the number of collisions that take place. In other words, in order for a reaction to take place, the particles actually have to collide with each other. Okay, so what does that mean? Well, if we increase the concentration of our reactants, we're going to increase the number of collisions, and that's going to increase the rate of the reaction. Okay, if we were to increase the temperature, we're increasing the average kinetic energy of the particles, which is going to increase the number of collisions, which is going to increase the rate of the reaction. So anything that increases the number of collisions will increase the rate of the reaction. So if we were to look at this reaction as an example, okay, the reacting species have to collide not only with each other, but they have to collide with each other in the right orientation. So as an example, if we had carbon monoxide and it comes in contact with oxygen in this orientation, they're not going to react with each other. But if the carbon monoxide were to collide with the oxygen in this orientation, then the reaction does take place. So not only is it the collisions have to occur, but the collisions have to occur at the right orientations. And the collisions have to have enough energy for them to be effective collisions. Okay, well, what does that mean? Well, if we have reactant A and B, and they collide with each other, and they even collide with each other in the right orientation, but they don't have enough energy, they're not going to react. Okay, if we kind of think about this potential energy diagram here, if A and B were to collide with each other, but they don't have enough energy in order to reach this point here, which is called our transition state, we're not going to be able to break the bonds in the reactants. So we're not going to be able to make new bonds for our products, and the reaction isn't going to progress. But if the reactants do have enough energy, then the bonds on the reactants can break, atoms can rearrange themselves, new bonds can form, and products can be produced. So we're talking about what's called activation energy, which is sometimes called EA for short. Okay, this is our activation energy. And if we were to increase the temperature, that's going to increase the kinetic energy of the particles, which will enable those particles to get up and over that hill and produce products. So activation energy. Activation energy is the minimum energy required in order to form effective collisions, in order for the collisions between particles to actually form products. And when we look at this point here, this is called our transition state. It's kind of at the top of this activation energy hill. So in other words, if we have our reactants and the reactants have enough energy to get up to the top of this hill, we're going to be able to break the bonds on the reactants, rearrange the atoms into our products, and then form new bonds and make our products. If we increase the temperature of the reaction, we're increasing the kinetic energy of the particles, more particles will be able to get kind of up and over this hill, and the rate of the reaction will increase. So if we were to look at this graph, okay, T1 is a lower temperature. T2 is a higher temperature. Now, if we have a reaction at a lower temperature, more of the particles are going to have a distribution of energy here, and less of the particles are going to have enough energy to get up and over that hill. But if we increase the temperature of the reaction, that's what this red graph here is showing us. We're increasing the distribution of the kinetic energy for the particles, and more particles are going to have enough energy to get up and over that hill. So increasing temperature increases the kinetic energy of the particles, which increases the effectiveness of the collisions, and it's more likely for us to make products. So let's look at this reaction, okay? We're starting with N2O5. There's our reactant. Now, in order for this reaction to take place, 102 kilojoules of energy per mole has to be added in. That's the minimum energy to get the reactants to produce our products. Now, our products are here. Our products have more energy than our reactants had. This value here is telling us the energy difference between the reactants and the products. It's essentially our delta H value. So we can decide whether or not this reaction is endothermic or exothermic, because here are the reactants and here are the products. So the first question says, what is the enthalpy for the reaction? Okay, that's the difference between the products and the reactants. So that value is 55 kilojoules. Now, there should probably be a positive sign here just to kind of show that the products have more energy than the reactants had. It's okay that it's not there, but it might be better to have a little positive sign here. The next question says, what is the activation energy for the reaction? Well, the activation energy is the amount of energy required to get up to the top of our hill. So in this case, our activation energy is 102 kilojoules per mole. That's the minimum energy to have effective collisions to produce products. Now the reaction says, is it exothermic or endothermic? Well, our enthalpy value is positive. Our products have more energy than our reactants had. So overall, energy had to be added into the reaction. So the, oh, sorry. What did I forget to do? What is the activation energy for? Oh, for this, sorry, I didn't read what it said. For this reaction, okay, that would be, I should have read the question. That would be the activation energy here. Okay, well, that's the difference between the 102 and the 55. So for the reverse reaction, we're just reading the graph in the reverse direction, 102 divided by 55 would be 47 kilojoules per mole. Now, is the reaction endothermic or exothermic? Going in the forward direction, it would be endothermic. The products have more energy than the reactants have. And then on the graph, we want to show where the transition state is, and the transition state's always going to be at the top of our hill. So the transition state would be here. And essentially, this is where the bonds in the reactants are broken. The atoms are going to be rearranging themselves, and then new bonds are going to be formed, and we're going to have our products here. So let's look at another graph. And I'll give you a couple minutes. Okay, it's the same concept. The graph looks a little bit different. Here are the reactants. So we've got nitrogen dioxide reacting with carbon monoxide. Here are the products here. We're going to produce nitrogen monoxide and carbon dioxide. So here's our equation. We want to figure out first, what's the enthalpy for the reaction? So it's products minus reactants. Then we want to figure out what the activation energy is for the forward reaction. So that's from here to here. Then we want to figure out the activation energy for the reverse reaction. So that's from here to here. Then we want to decide if the reaction's endothermic or exothermic. So here are the reactants. Here are the products. Is energy being absorbed or is energy being released? And then show where the transition state would be. All right, so let's see how we did. What is the enthalpy for the reaction? Okay, and if it doesn't state otherwise, we're reading the reaction in the forward direction. So that's the products minus the reactants. So that's negative 266 kilojoules per mole. Our products now have more or less energy than our reactants had. What is the activation energy for the reverse reaction? Okay, well, now we're going in this direction. Well, we know this value is 260 or 226. We know this value is 134. So the activation energy for the reverse reaction is going to be the sum of these two numbers. So our activation energy, what am I doing? The activation energy for the forward reaction is 134. Sorry, I'm getting ahead of myself with these. So the activation energy for the forward reaction is here. The activation energy for the reverse reaction is the sum. So 136 plus 134. So that's where that 360 is coming from. Is the reaction exothermic or endothermic? Well, our products have less energy than our reactants had. Our delta H value is a negative value this time. So the reaction's exothermic. And if we want the transition state, it would be at the top of the hill. So that would be right up along here. So questions on these potential energy diagrams? Do they make sense?
Yeah, they probably are just going to take a little while to, I personally have some trouble with reading like graphs sometimes, so I'll probably just have to practice a little bit with this.
Yeah, and everything takes some practice. So we just need to remember that here are the reactants, okay? Here are the products. We want to get from the reactants to the products, but they can't go straight from here to here. We have to add energy in so that we can break the bonds on the reactants. We have to rearrange the atoms, and then we make new bonds here. And the difference is, are we adding more energy in to break the bonds, or are we getting more energy back when we make the bonds? Exothermic processes, we get more energy back than we had to add in. Okay, we can read the reaction in the forward direction by going kind of from left to right on the graph. we can read the reverse reaction by going from right to left. And the activation energy is, from your starting point to the top of the transition hill. So the forward reaction would go from here to here. The reverse reaction would go from here to here. And your enthalpy change is just the difference between, where you end up from where you started at the beginning. All right, so, what did that say? Nah, we're not going to do that. I think we're not going to shove that in there today. Okay, so we have finished almost all of chapter 17. We have just a little bit more to do. I don't want to shove it in the next couple of minutes. So we will start at that point tomorrow. What I'll do at the beginning of the period tomorrow is I will, again, give you a couple of practice problems like what you'll see on your test on Wednesday. So hopefully if you spend a little bit more time tonight studying, the more practice you do, the better off you're going to be. So if I give you a couple more practice problems to do tomorrow, you should be in good shape for your test on Wednesday. And then we will finish up chapter 17, and then we're going to go backwards back to chapter 13. And we'll spend some time tomorrow and then all of Thursday starting to work on chapter 13. And we'll also start kind of talking about the next test, which is next week. So does anybody have any questions? Let's start here. Any questions on what you're going to see on your test on Wednesday? Pretty clear on what to expect?
About how many calculations will there be on the test?
Well, there are 6 open-ended questions that you have to show your work on. And then if there are any calculations you need to do in part 1, they're fairly simple calculations. So there are 6 more complicated calculations and maybe a couple extra simpler calculations. Okay. All right, questions on stuff we did today? All right, so again, remember that you have a lab that if you haven't finished yet is due tonight by 11:59, and you have a handful of homework sections that you need to get done as well. And you need to start getting yourself ready for your test on Wednesday. So I'm going to first stop sharing and